Okay, so before proceeding to the hard statement about the inertia being unramified at infinitely many places, implying that we have good reduction, let me say we have to describe the structure of the m-Torsion of the special fiber of the Neron model. Okay, so so what we'll do is so this is the structure of the m-Torsion of the reduction of the Neron model. Okay, so here we're going to have k over qp, an algebraic extension. Okay, a over ok. This is going to be the Neron model of its generic fiber. And then we're going to let, okay, so then we're going to do some notation here. So that A bar, so this is going to be AK, so this is the special fiber. This is going to be the special fiber. Okay. All right. And then, so we just want to make some observations about this. So here, just as a reminder that the k-bar points here, this is the same thing as the k-bar points of the generic fiber, which is the same thing as the OK-bar points of the Neron model. And the little k-bar, so little k is so let's do this. Little k is the residue field. The characteristic of this is P. Okay, so that's what we have. This is the Neron model. This is the special fiber. I should have maybe not offset that, but whatever. And then this is A bar of K bar. Okay, so this is via the Neron mapping property. Okay, and I guess these are technically isomorphisms. Okay, so okay, so now we're going to get to the first statement here. So we need to recall this the Chevalley-Rosenlicht theorem. So Chevalley. So the question is that we're answering here is, let me just as a reminder, is we want to know about this. Okay, so we want to know what the size of this thing is. Okay, and this, remember, denotes the k-bar points of that. So so this is a theorem about connected solvable group schemes. So we have the following, that H looks like the connected, so if we take the connected component of the identity of the group scheme at the bottom, right, so we have an extension like this, right, so there exists an extension like this. This is an Abelian variety. Over K. And this part here, so this is an affine algebraic group. And H is so in general, if this is just solvable, it would be a semi-direct product. But so this part here is a torus, and this part here is a unipotent. This is the unipotent group. Okay, so torus is just a product of GMs, and an element is unipotent if the identity, that element minus the identity, is nilpotent. Okay. And so we're just thinking of these as matrices, okay? And so, okay, so we have this exact sequence. This is of algebraic groups over K, over this field K. Okay, so now we're going to apply this result. Maybe I can say, let me just fix some notation, because this will come up later. So I just need to talk about the dimensions notation. So the dimension of A is going to be G. The dimension of B is going to be B. The dimension of of u is going to be little u, and the dimension of s is going to be little s. Okay, so this is, I'm going to refer to these later. That's what they mean. There are these parts of this Chevalley-Rosenlicht decomposition here. Okay, so all right. So now let's look at the k-bar points of that sequence. Okay, and we have the following. So we have this sequence. So we take h k-bar, a bar k-bar, b k-bar. Okay, so we have this exact sequence of groups, and since h of k-bar is uniquely, is just m divisible. So every element can be written as m times some other element. So this is okay. So this condition here is what's important for when you have an exact sequence. You can take the torsion, and then you want it to still be exact, right? So we get the following exact sequence. So it says 0. So we take h m. So a bar 0 of m, b of m to 0. So in general, you have to, let me just say a little bit about this m divisibility. In general, you have to worry about this surjectivity here, right? And so what happens is, so let me just say, so like you have to use the fact that elements in the kernel of this can be written as m times some other element, to like take a preimage of a torsion point here and show that you can modify it to get it to look like a torsion element preimage. Okay, so that's the idea. The left side of the exactness comes for free via representability of torsion by z mod m dash. Okay. Representable functors preserve limits, and this one here is a limit. Okay, so all right. So other things is that this decomposition here, the unipotent things, that doesn't have torsion. So this is the same thing as u of m. Okay, so okay. So now this proves some business about. So let me just say what this does. So this proves the following. So this proves that here that a bar, if I take the connected component and I look at the m-Torsion, so this part here is a free group of dimension 2 times the dimension of this, and then this one here is a free group of dimension s. So this thing here is isomorphic to z mod ms, and this is isomorphic to z mod m 2b. Okay. Yeah, and then this is abelian, and so this thing splits here. Okay. So, all right. And so what else? So okay. So this kind of like describes half. So what are we trying to do? We're trying to describe this torsion. This describes half of it, at least in terms of the connected component. And what do I mean by half of it? Okay, so this is, let me just kind of like circle this. This is half of what we want. Right, so to get the other half, well, what do we use? So we use that a bar, right? So this is for the other half. Is that gray now? Maybe it's gray. Maybe I'm crazy. Okay. Is that gray? Am I like tripping? Okay. Okay, let's ignore the grayness. Okay, so let's take these group schemes here. This thing has a connected component, and then you can always quotient by this component. This is I guess called the connected Étale sequence, right? And so what we can do is we can take the K. So we have this exact sequence, and so then we can take. Yeah, that's totally gray. Ah, so you can even see it. Okay, so we can take. Oh, this is gonna look weird next to the gray. Okay, so we can take the m-Torsion of the sequence. So to get. Okay, and then we're going to use that uniquely p-divisible thing again to get 0 a bar 0 of m. Oh no, we don't get the p-divisible thing here. So surprise. Okay, so here a mod a. So I bet you thought it was p-divisible. This thing was divisible. We're not using that. So this is maybe not surjective. Okay, this thing. Maybe not surjective, but that doesn't matter. That's not going to stop us, right? So what do we do? Well, okay, so it's an extension of something, whatever the image of this is, and then by this kernel thing. So so notice that so the image. So here the image of this thing. So oh god, I'm going to write it out. Okay. Blah 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 blah. Okay, so the image of this is some subgroup of, so this is a subgroup of a mod a bars, and you get a bar. Okay, so this is this here. And so this thing, and hence divides, a bar, so the index here. Okay, so this is like the k-bar points of that thing is how we can count that. So sorry, and hence the order of this divides this number here. Okay, because you know you have a subgroup. Okay, and so this proves the following. So this proves that the following. So this proves the following theorem. It says that so this proves that one, that this is isomorphic to S plus 2 times B. Okay? The other thing that it does is that okay, we have this okay, so that's what we proved previously. The other thing that we do is that this is an extension of a finite group. Let's say GM, whose order divides this index. Maybe this is like a really long-winded way of doing this, right? By this torsion here. Okay, and then we're going to use this for counting. Okay, so this is oh, I should have done that. Oh, let's go to the color here. Okay, so this is what we actually want, and then I should have like said that the divides this. Okay, so like I should have done this. This is the second part of what we want, but I forgot to do that. Anyway, so this is the structure. Okay, so let me remind you what we're doing here. We're talking about the structure of this thing, and I'm going to apply this, right, in order to deduce that to get properness. So to show that when we have torsion being unramified for arbitrarily large n, that the special fiber is proper, and the special fiber of the Neron model is proper, and that is going to allow us to show that there's good reduction. Okay, so that there exists an Abelian scheme over R whose generic fiber is our given scheme, given an Abelian variety. Okay, and so that's part of the. This is going to go into the proof.